In this video, I'm going to be describing what slope fields are and how we can use them to find visual solutions to some differential equations that are sometimes hard to solve. For example, solving this differential equation may be difficult, but what we can do is instead come up with a slope field that can represent all of the possible solutions. So a slope field is really a bunch of slopes represented at individual points. So if I take this differential equation, which says that the slope, dy over dx is the slope is the x-coordinate minus the y-coordinate. So if I plug in coordinates, then I get the slope at that point. And if I do that a bunch of times on a grid or a coordinate plane, I can represent the slope at any point, and I can do it as much as I want or as little as I want. But the more that you produce these slopes at each point, the better idea you have of the behavior of the graph that is the solution to the differential equation. So if you solve a differential equation, you get that antiderivative function. And this is essentially the slopes of that antiderivative function. But remember, when you solve a differential equation, you get a general solution. And those general solutions are representing all of the possible solutions to that differential equation. So doing it by hand can be pretty rigorous and take a long time, especially if you create a very big slope field. But luckily, nowadays, there's slope field generators that people have created for us. So if you just type in the differential equation, it comes up and gives us our slope field. So what that slope field generator is doing is taking the coordinates and evaluating the slope at every point and then sketching out a little segment that best represents that slope. For example, if I plug in 2, 4, so my x value is 2, my y value is 4, then 2 minus 4 gives me a slope of -2, and so I can draw a little segment that best represents a slope of -2 going down over 1. So that's what a slope field is. And what we can do with a slope field is draw best fit lines that somehow follow these slopes, and that would be a graph that represents a solution to the general solution to this differential equation. But there are many, so you can draw all kinds of lines. As long as it fits that slope field, that's one possible solution. So you can try out this next one, or you can use the slope field generator to do it. But you're just plugging in coordinates, and the answer that you get represents the slope at that point. And the slope is the slope of the solution graph to the differential equation. Let's look at it backwards. What if we are given the slope field? Then can we choose a differential equation that is best represented by that slope field? So in this case, it's just a lot of guessing and checking. So you can plug in coordinates into each of these differential equations and see if the resulting slope matches the slope that's sketched out at that point. So for example, if I want to check out the coordinate right here at 4, 2, that point. So x is 4 and y is 2. So if I plug those values in, well, if I do that, I get -8 for this differential equation. Well, that slope right there is definitely not a negative slope. That's a positive slope. So this differential equation is not possible. Let's try out C here. Check the same coordinate. Sometimes you can use the same coordinate to disprove some of these differential equations. Sometimes you have to choose a different coordinate. So let's try out the same one. If x is 4 and y is 2, then that would give me a slope of 2. And that's not quite up 2 over 1. It would be a little bit steeper slope drawn there. This looks like it's maybe up 1 over 1. So C is not it either. Let's try out the differential equation given to us in B. So again, if x is 4 and y is 2, that would be a slope of 8. And that slope is definitely less steeper than 8. So that's not it either. Let's see why D is the best solution, or best differential equation. If I plug in 4 for x and 2 for y, that would be 2 over 4, which would be 1/2. This looks like it's about 1 over 2, maybe. Maybe it's too close. So in this case, we might have to check out a different coordinate. Sometimes using coordinates that lay on the axes is a good place to do it. So because we're not given any slopes here on the y-axis, that's implied that the slope at that point is undefined. If you have a horizontal line drawn as your slope, that would mean that your slope is 0 at that point. So let's try something on the x-axis. Let's try 4, 0. So if I plug in 4 for my x and 0 for my y, I get 0. So that holds up. Let's just try out one more. Let's see if we can get a negative slope here. If I plug in -2 for, so -2 for my x, +4 for my y would give me a slope of -2. And that's sketched out. That looks about like it's going down 2/1. So D is our better answer there. One more time, you can do the same thing. Try out some coordinates, plug them into each of these differential equations, and see which one of them best represents the slope field. And in doing so, hopefully you choose C. So that's an introduction to slope fields. They're representing possible solutions to the differential equation.